This video provides a brief overview of quite a lot of topics that crop up mostly in the Part 1B Fluid Dynamics course here at Cambridge. So if any of these are especially unfamiliar to you, I can strongly recommend reading up the notes on that course, and we'll just do a little bit of a whistle-stop tour of some key concepts in fluid mechanics. Now, all of continuum mechanics, let's just skip back to the previous slide. All of continuum mechanics rests on the so-called continuum hypothesis. And this is a bit philosophical, but it basically says that quantities like the velocity field U, pressure field P, density make sense because we can take a small little parcel containing many different fluid molecules, and we can average over small regions to get values. i.e. density makes sense because we can take a small fluid parcel and average over the amount of molecules in there to work out the local density at that point. And so we basically need fluids, for a fluid we need to have particles that are packed sparsely enough so that individual molecules can move, otherwise we wouldn't have a fluid, we'd have a solid, but we need them to be packed densely enough such that these averages make sense. Okay, there's two ways of approaching continuum mechanics. When you have one of these little control volumes or parcels, you might actually want to follow its evolution in time. It might move, it might change shape, might change in properties like density or pressure. And in order to follow what's happening as time evolves, you use something here called the material derivative. And the material derivative, which is also known as a convected derivative, has two components. It has a component due to things just changing in time because they change in time, this partial derivative with respect to time here, but it also has a u dot grad or advective term. And this encodes changes in material properties due to this fluid parcel moving, because u here is the velocity field. So this parcel might move to an area where the material properties are different, and therefore they might vary, not because they're varying purely with respect to time, but because this parcel is now in a different place. This can get a bit complicated, so perhaps the easiest way to view fluid mechanics for many different contexts is an Eulerian approach, where we fix a point in space and we say, what's the pressure here? What's the density here? And this will vary in time, both due to it just varying in time because the system might be changing in time, or due to fluid particles moving in and out of this region X. And so this is the approach we're going to take for most of our problems. Okay, so the first equation, or the first set of equations we're going to talk about come from conservation of mass. So let's consider a little blob, a volume V, which could be any shape. If we integrate the density over this volume V, we get the amount of mass in this volume. And that has to be matched by the flux of mass coming out of the volume. And so if we integrate the density times the velocity all over the surface of this volume V, it's got to match the rate of change of total mass, or else mass is being created or destroyed, which we can't have. So let's play around with this integral expression. First thing we'll do is we'll pull this time derivative under the integral, so we get d rho by dt, dv, plus over the surface rho u dot ds equals 0. Then we'll apply the divergence theorem to this second integral and just end up with an integral over the whole volume of d rho by dt plus div of rho u dv equals 0. But v is arbitrary. We said earlier that v does not necessarily depend on, we can just make any choice of volume we want. So that implies that actually this quantity within the integral must be 0. So d rho by dt plus div of rho u equals 0. And this is the equation of conservation of mass. We can write it more suggestively in the form d rho by dt plus u dot grad rho plus rho div of u equals 0. And notice that this here is material rho by material t. So d rho by dt equals 0 implies and is implied by div u equals 0. So if the density isn't changing in time, flow field is what we call incompressible. An incompressible flow field is probably most flow fields will deal with in this course, except when you start doing some waves problems. Most fluids can be treated as incompressible. Water is effectively incompressible. Air is not, because it's thanks to air being compressible that you can hear me right now. But for most of the fluids you'll deal with in part 3, we will have incompressible cases. So when a fluid is incompressible, div u equals 0 in 2D allows us to, we can write the velocity field in the form d psi by dy minus d psi by dx, where psi is the stream function. And you can see straight away that this expression here satisfies incompressibility. And the handy thing about the stream function, it's got many useful properties, which I suggest you look up if you're not familiar with it. But the most important thing about the stream function is, skipped a slide there, curves psi equals constant are called streamlines and are tangent to the flow. And we'll revisit that later on. Okay, the next equation we need comes from conservation of momentum. All of this is based on something called the Cauchy stress tensor. So momentum, remember in bog standard mechanics, is mass times velocity, and here we've essentially got a continuum mechanical version of change in mass times velocity. Because this is a change in velocity with respect to time, and this is a bit like a mass, and that's got to balance a force, because forces balance changes in momentum. We know that to be true. So the Cauchy stress tensor, the divergence of the Cauchy stress tensor gives us a force, and we'll talk about what this is in a second, but we might also have body forces. So these are forces like gravity that act on the fluid, and they're forces per unit volume. Lovely, okay. So we haven't yet got an equation because we don't know what this Cauchy stress tensor is. So we need to do something called get a constitutive relation. And this allows us to write Cauchy stress tensor in terms of quantities that we actually care about or that we actually know. And so in this case, in fluids, the isotropic part of the Cauchy stress tensor is minus P, where P is the pressure, and D here is the deviatoric part. Now, deviatoric just means that the trace is 0. Okay, we still haven't specified what this deviatoric part is though, and that depends on the sort of fluid that we're modelling. If we're modelling a Newtonian fluid, which is what we're dealing with most of the time, we're modelling an isotropic fluid. So one of the assumptions we make is the fluid is isotropic. It's the same everywhere. Its properties don't vary in space. The dynamics are local. That means that something happening a long way away does not influence the behaviour of the fluid at a given point. And memoryless, this means the history doesn't change the fluid properties. The deviatoric stress, so this D here, is independent of displacement. If we go back to think about fluid particles, if we've got one fluid particle here and later it's moved to here, this distance or this change in position here is a displacement. And so fluid properties don't depend on where a fluid molecule started out. They might depend on how quickly it's moving and which direction it's moving in, but it doesn't matter where it started out. And so deviatoric stress is independent of displacement, but is linear in the rate of strain. And the strain here, this is the Cauchy rate of strain, so brackets, tensor. And it's equal to the symmetrized gradient of the velocity field. Okay, so if we plug this in, we get the Navier-Stokes equations. So rho du by dt is equal to, well, this pressure comes out to be minus grad P if we take div sigma, and div D is just going to be mu div of grad U plus grad of div U. This is 0 when we're dealing with incompressible flows, and this is just the Laplacian. And here we have the familiar Navier-Stokes equation. Lovely. Okay, that needs to be solved with boundary conditions, and boundary conditions can be grouped into two main categories. Kinematic boundary conditions come from matching fluid velocities with what they're next to, be that solid boundaries or flexible boundaries or other fluids. Basically, at a boundary with normal n and velocity capital U, we just have to have u dot n, little u dot n, this is the fluid, the normal velocity of the fluid, has to match. I.e., we've got a wall here that's moving speed u here, fluid has also got to be moving at speed u or else it will separate. So that's our kinematic boundary condition. Another way of composing this, we've got a boundary that's just defined implicitly, like so. Then the material derivative of that boundary is 0. Dynamic boundary conditions are situationally dependent, and these come from things like in viscous flows. So I'm just going to list some examples here. These don't always apply, but in viscous flows we have a no-slip boundary condition. So U is equal to 0 on a stationary boundary, i.e. it's not just the normal component that matches, it's both the normal and the tangential component. We have things like continuity of stress, normal stress more specifically, i.e. sigma dot n, it's the same either side of the boundary. We could have continuity of pressure, P plus or minus equals 0. We can have more complicated things. So for example, with surface tension, stress is no longer straightforwardly continuous. See the Young-Laplace equation for an example of what the boundary condition is on the normal stress when you have surface tension. Okay, that was a bit of a whistle-stop tour. We'll generally introduce boundary conditions as we need them for different problems. Right, let's just look at two simple examples of viscous flows. Here's one called plane correct flow. We've got two planar boundaries that I've drawn in an attempt to be parallel but have not come out to be particularly parallel, separated by a fixed distance h, and this top one is moving at velocity v and this bottom one is stationary. And the flow just has a linear profile. So because we're dealing with a viscous flow here, we have no-slip boundary conditions. And the no-slip boundary conditions, as discussed before, tell us that up here, u is equal to v, and y equals h, and down here, u is equal to 0, and y equals 0, and it varies linearly between these 2 points. And all the flow is horizontal, and this is just one of the simplest viscous fluid flows that we can deal with. Poisson flow is driven by chain or gradients in pressure. So again, we've got a channel with two walls. In this case, both of these walls are stationary, but they're separated by a fixed distance h. And we've got pressure P1 here and P2 here, separated by a horizontal distance L. And now the flow profile has to satisfy no-slip boundary conditions on both boundaries, so u is 0 on both boundaries, and you get a parabolic flow profile here, with fluid being driven from areas of high pressure to areas of low pressure. So these are the kind of two canonical viscous fluid flows. You'll see them pop up all over the place in lots of different courses this year. Okay, The next important topic is vorticity. Now, vorticity, omega, is defined to be the curl of the velocity field. And we can derive this thing here that's called the vorticity equation, derived by taking the curl of Navier-Stokes. Okay, let's look at the importance of the different terms. So vorticity is a really important concept, especially in the study of inviscid flows. So the first term here is just, how does vorticity change in time? Well, it changes by advection. Vorticity is carried along by fluid. There's also a term here called vortex stretching, which is a consequence of conservation of angular momentum, because in a hand-wavy sense, vorticity is just a measure of the rotation of a flow. It's more subtle than that, but that's a pretty hand-wavy description of it. So this thing here is called vortex stretching. Conservation of angular momentum. We get a diffusive contribution. Viscosity leads to the diffusion of vorticity. And then we get this body force term, which is usually zero. Actually, the curl of the body force is normally zero, so very rarely affects the vorticity. Okay, but this has a few interesting corollaries, especially when it comes to flows where the vorticity is zero. These are called irrotational flows. Specifically, if irrotational and inviscid, so the viscosity is zero, our vorticity equation just says d omega by dt is equal to omega dot grad u. We'll ignore the body force. So if omega equals 0, t equals 0, omega equals 0 for all time, i.e. an initially irrotational inviscid flow remains irrotational for all time. The only way vorticity is created or destroyed is through viscosity, so through viscous effects at boundaries, for example. If you look at the topic on boundary layers, that's a really helpful way to see an example of this in play. But these flows where vorticity is zero have another handy property. Much like incompressible flows have a stream function in 2D, irrotational flows have this thing called a velocity potential. Because the curl of a gradient is zero, we can always write the flow field as the gradient of some scalar velocity potential phi. This thing here comes from Navier-Stokes, replacing u with grad phi, and we just find that, and this is called the Bernoulli quantity, and this is just conservation of energy, basically. This becomes very handy for solving a lot of different problems. If you want to see more about that, read up one of the middle chapters in the Part 1b Fluids notes. But the final thing, if we are irrotational and incompressible, then div u equals 0 implies that del squared phi equals 0, so we just have to solve Laplace's equation for a velocity potential. That could be incredibly handy. It helps us solve an awful lot of problems. So, speaking of solving problems, we'll close this out by solving an example sheet question from the second year fluid dynamics course. Oh no, sorry, the third year fluid dynamics course, which you can access online. Okay, so the first thing we need to do is confirm that this flow is incompressible. So we just need to take div u. And this is going to be d by dx of alpha x minus 1/2 omega y, and add it to d by dy of minus alpha y plus 1/2 omega x, and show that this equals 0. Well, this is just alpha, and this is minus alpha, so this does indeed equal 0, so we're incompressible. Now we need to find its stream function, and recall that the stream function is defined such that d psi by dy is equal to u, and d psi by dx is equal to minus v. Okay, so let's do this bit first and see that d psi by dy is equal to alpha x minus 1/2 omega y. So psi is just going to be alpha xy minus 1/4 omega y squared plus some function of x. d psi by dx is just going to be alpha y minus plus f prime, which is going to be equal to minus v, which is just alpha y minus 1/2 omega x. So that implies that f is going to be minus 1/4 omega x squared plus some constant, which we'll log take to be 0. We can always do this with stream functions because only their derivatives matter. So we'll log take that constant to be 0, and that implies then that the stream function for this problem is psi equals alpha xy minus 1/4 x squared plus y squared. Lovely. Also, there's an omega there as well. Now remember, streamlines are lines psi equals constant, so psi equals k are streamlines. Let's see whether we can find conditions on these streamlines to be elliptic or hyperbolic. So we'll multiply both sides by -1 and just get 1/4 x squared plus 1/4 y squared minus alpha xy is equal to minus k. Lovely. Completing the square on x, we can have, well actually let's just multiply all up by 4 just to make it look a little bit nicer. X squared plus y squared, sorry, there's an omega here as well, and an omega there, minus 4 alpha over omega xy is equal to minus 4. Well, this is still just a constant, so I'll just redefine it to be c. Okay, complete the square on x. X minus 2 alpha on omega y all squared plus 4 alpha squared over omega squared y squared, oh sorry, minus plus y squared is equal to constant. And this then can be rewritten as x minus 2 alpha over omega y all squared plus 1 minus 2 alpha over omega all squared y squared is equal to constant. Now you can see here, if alpha is greater than 1/2 omega, this has a certain behaviour, so that this is a minus here, so this is basically a capital. Let's change variables. So the best way to look at it is to change variables and say that this is, say, capital X squared plus 1 minus 2 alpha over omega squared y squared is equal to c. And this looks a lot like an ellipse if this term here is positive. It looks a lot like a hyperbola if this term here is negative. And these two correspond to the two cases where mod alpha is either greater than or less than 1/2 omega. Great. So we've shown that. Perfect. If you want to read more of this, there's a little pink book by Gray Worcester called Understanding Fluid Flow, which covers quite a lot of the fundamentals of fluid mechanics. And there's also the notes from the Part 1B course available for free online. Bring along any questions to the in-person session, and I'm sorry that was such a whistle-stop tour without all that much detail.